All right, pre-calc part 2 of section 8-4 notes, page 18. I'm on the back side, part 2 of 8-4 notes. Need a little better pen. Part 2. Looking ahead here, example 4. I might like that. Let's see if this works now. There we go. Let it adjust the light. For part 2, this first problem here, it's a little bit above and beyond what we need to do here. You got cotangents and you got cosines squared. A couple ways you could approach this one, but I think the intent was like to divide cotangent. You got two cotangents, you divide by a cotangent. The cotangents would like cancel each other out. Cotangent x, you get cosine squared x equals 2. I'm not a fan of this kind of problem right here. I'm going to give you two substitute problems. I'll give you two substitute problems, more of the style of what we're going to be doing. So like if I gave you cotangent x plus 1 equals 0. Cotangent x plus 1 equals 0. Really simple equation, I know. But if I go cotangent x is equal to negative 1, you got to remember that's the x number over the y number. What they're basically saying is that they're the same. And the only time that happens is when we get root 2 over 2 divided by root 2 over 2, 45, 45, 90 triangles. However, if it comes out to be negative 1, then that means either the top one was negative or the bottom one was negative. One or the other was negative. Either the top was the negative or the bottom was negative, but not both at the same time. So the only way that can happen, you got to think 45, 45, 90 triangles. Root 2 is over 2. 45, that's the only time when the legs, the x and the y, end up being the same number divided. But we want them to be opposite signs. So that would be root 2, quadrant 2 and quadrant 4. Oh, 4. I almost wrote that wrong. 2 and 4. Here and here. 45, 45, 90 triangles. 45, 45, 90 triangles. This would be a negative root 2 over 2, positive root 2 over 2. This is a 1, obviously. 1. Positive root 2 over 2, negative root 2 over 2. But when you take the x divided by the y, you get negative 1, or this x divided by the y. So what two angles are these? You got to start from 0. How many degrees is this? How many degrees is this one? So x is going to equal 135 degrees, and x is going to equal 315 degrees. So both those answers are solutions to it. You can get more than one solution. We showed one on the other page where you got 4 solutions. Let's switch it over to radians now. If I gave you 4 sine squared theta minus 3 equals 0. Well, you got to add 3 to the other side and then divide by 4. Add 3, then divide by that 4. You get sine squared theta positive 3 divided by 4. Then you square root both sides, and you're going to get sine, I almost said sine squared, but just sine theta. The other side will say plus minus, and you got to square root the top and the bottom, and you get square root of 3 over 2. Now that means that's the long leg of 30, 60, 90 triangles. Square root of 3 over 2 whenever it's sine or cosine, and you get square root of 3 over 2. Long leg of 30, 60, 90 triangles. So think of that, and it can be positive or negative. The long leg is when it stands up tall like this. Short leg here, long leg here. That's 60 degrees. So your reference angle has to be 60 degrees. That's square root of 3 over 2. That's another positive square root of 3 over 2. But it can also be a negative square root of 3 over 2 because it was plus minus. So it can be here and here, negative root 3 over 2. 60 degrees is the reference angles. But they want these in theta. They want these in radians as well. Since they use theta, we're going to put it in radians. So not 60 degrees, that's pi over 3. So my answers for theta are going to be pi over 3, and then over here, 2 pi over 3. At the 180 mark, that's pi. That's 3 pi over 3. So this is 4 pi over 3. And over here is 5 pi. those are my solutions. So wasn't crazy about the problem they gave us. So I gave us two little side questions here. Two little side questions so that we can just practice more and more of how we do this solving stuff. How about solving if you got to do factoring? So basically, we've done this before. If I give you like x minus 3 times x plus 2, and that was equal to 0, you set each one equal to 0, x equals 3, x equals negative 2. We're doing that same kind of thought, all right? That same kind of stuff. So where you have 2 sine squared x minus sine x, not sine squared, sine x minus 1, you have to think, you want to factor it the same way you would factor 2x squared minus x minus 1 equals 0. Since that's 2x squared, you know you got a 2x, that's negative 1. You know you have a plus 1 and a minus 1. You know when you add the middle parts, you want it to come out to equal negative x. So I think it's going to be negative over here, so that the middle is a negative 2x and then a plus 2x, and then a plus 1 here, and this would be x. So that's how that would factor. So how does that work with the signs? Same idea. It'd be 2 sine x plus 1 times sine x minus 1. And the same kind of rule here with factoring, set each one equal to 0, each parentheses. So 2 sine x plus 1 equals 0, and sine x minus 1 equals 0. And solve those two problems. All right, so this one I'm going to subtract 1 and divide by 2. When does sine of x equal negative 1/2? Well, when is y negative? Y is negative in quadrants 3 and 4. Negative 1/2 would be the small leg 30, 60, 90. So we're talking x. This is a 30 degree angle, negative 1/2. Negative 1/2. So these answers over here are going to be 210 degrees. And if we go all the way to here, 330 degrees. Now for this problem, I'm just going to add 1 to the other side. When does sine x equal 1? Well, if you can answer like 1 or negative 1 or undefined, but if you get 1, that means you're on one of the axis numbers. Now remember sine x, whenever they're asking sine, they're looking for the y number. When does it come out to equal positive 1? It's when you're up here. When you're at 0, 1. How many degrees is that? That's 90 degrees. So the answers for this problem are, where am I going to write it? X equals 210, 330, and 90 degrees. That didn't really go in order there. All right, last problem. So the last problem in our notes, it's a good trig problem. Notice it's got sine squared and cosine involved. So it kind of goes like what we did up here. It had cotangent and cosine involved. And you want to get it down to just either just sine or just cosine. So there's a way to make this all cosines. And that would be to switch this out. To switch that out. So you would use your trig identity sheet. And you go to that very popular sine squared plus cosine squared equals 1. Take the sine squared out and replace it. Subtract cosine. You would replace that with 1 minus cosine squared x plus 3 cosine x minus 3 equals 0. That's kind of a crazy problem. That would give me 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. I do have to combine like terms. Never mind. I was going to say, don't worry about combining like terms. But this 2 and this negative 3 plus 3 cosine x. Add that 2 and negative 3, you get negative 1. You want to factor it now. I want to divide everything by a negative 1, both sides. Like picture dividing this by a negative 1. Normally you wouldn't even draw this. Or multiply this side by negative 1, this side by negative 1. And make it positive. 2 cosine squared x plus 3 cosine x minus 1 equals 0. Factoring, very similar to the last one. I'm going to go 2 cosine x. Let's see. It's got to be positive 3 in the middle. That doesn't work. Uh-oh. Who wrote this problem? That doesn't factor the way they wanted it to. Maybe the sign is wrong here. To me, it should be a negative. Oh, that's because when I divided by a -1, I forgot to change these signs. There should be a negative, and that should be a positive. I was about to bail on this problem. When I divide by -1, everything has to change its sign. I only changed the first one. That's why I was stuck, and it wasn't going to factor it for me. Now it's going to factor for me. 2 cosine x minus 1 and cosine x minus 1 equals 0. So cosine x equals 1/2. Cosine x equals 1. If you set each one equal to 0. These solutions would be, oh man, I don't like this problem because it's a repeat of the answers. Almost the same thing. But it's the x is the short leg this time. So it'll go up like this. So it'd be 60 degrees, and in quadrant 4, 60 degrees up, 60 degrees, and 300 degrees. For this one, when is the cosine equal to 1? It's when you're at the 0 line right here. When you're at 1, 0, the x number, or cosine is asking what the x number is. Sine asks what the y number is. So when does it come out to equal 1? When you're at 0 degrees. When you're at 0 degrees. And that could be an answer there. If they're including it, you can say 360 degrees. Sometimes they say before 360. Sometimes they say more than 0. So you can count that as 4 answers. 0 and 360 is really the same spot, the same location though. I'm not crazy about leaving you with just that kind of a problem there. Well, let's see if I could squeeze in one more example. Oh, helps if I have a pen that works. Let's go. How about secant squared theta minus 2 equals 0. Secant squared theta minus 2 equals 0. Add 2 to the other side. Square root it. Secant theta equals plus minus root 2. Plus minus root 2. So remember, secant is 1 over cosine. So I got to do the reciprocal over here. If I rationalize it, then basically what we're saying is square root of 2 over, well, I should say, if I do cosine here and I do the reciprocal of the other side, did that wrong. Square root of 2 over 2. When does x equal square root of 2 over 2? The 45-degree angles in here. So it'd be like pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. All right. I'm out of time. Kind of rushed through that last one, but I'm just trying to give you some ideas of what they need to do. The secant one, when I change the secant to cosine, I do the reciprocal of the other side. So the plus minus square root of 2, I should have done 1 over the square root of 2. I shouldn't have made this 1 over cosine. I should have just left it cosine. Don't mean to throw you guys for a loop on that one. All right, guys, I'm going to wrap it up right there. That's as many examples as I can. Obviously, I could maybe take a little more time and answer more questions. In class is always better than just watching this stuff online.